Hello, F Sharp. Welcome back. We are continuing our journey of writing an incredibly fast dictionary in just F Sharp. Now, last time when we left off, we added Fibonacci hashing to our dictionary. And what that was critical for was to make our dictionary more robust against patterns in the keys that are being used in our dictionary. So we've made that upgrade, and now we're going to start focusing back on performance. Now, things are going to get a little murky here, and we're going to unpack why. So if some of these benchmarks look a little weird, and when you run it, it seems to give different results, don't worry. We'll get into that. But what I'm wanting you to note right now is this is the results from our Fibonacci hashing dictionary compared to the .NET dictionary. And what we are seeing is that for integer keys, we are doing extraordinarily well. In fact, we are faster than the .NET dictionary in each of these benchmarks. Now, before you just say like, hey, this is just better, realize I've condensed down the number of benchmarks we are looking at just to make it easier for me to present to you in the real world. If I was to actually recommend this for a very large deployment, I would have a much more extensive suite of benchmarks. So I don't want you to think like, oh, this is all you have to do this professionally. No, this is an educational resource. And you can actually go and look at the Git history of this repo to see all the different varieties of tests that I was using. But these tests illustrated the things that I thought was the important things for us to focus on. So right now, it appears that our dictionary is faster for integer keys. When we look at string keys, though, we are slower. We're slower at 10 entries, at 100. We're faster at 1,000, much slower at 10,000. Now, this is kind of scattered all over the place. This is kind of strange. And if you look at, why on earth would we be so much faster at 1,000 than much slower? And part of the hint is if you look at the cache misses and the branch mispredictions, when we look at 1,000 entries, we see, oh, it's going to be hard for you to see. We see over here in the cache misses that we are faster. We have more cache misses, but we have far fewer branch mispredictions. At 10,000 keys, we again have more cache misses and proportionally a whole lot more branch mispredictions. And our number of branch instructions is just far, far larger. And there's this allocation going on here. So some strange things going on. But the important thing to note is that we are much slower for keys. What is going on? How is the .NET dictionary faster? That's a great question. And actually, we are going to go and look at the .NET dictionary. And the way we're going to do that is we're going to come to this lovely website, source.net, and search for the generic dictionary. And the way we're going to do that is in system.collections.generic.dictionary. And this is exactly what I did when I was writing this myself. I was writing the dictionary. I just looked at Wikipedia and how it described the way dictionaries are supposed to work. And I was also citing the work of Multi, who gave the presentation that I will keep referencing here on C++. And so in order to figure out, like, why am I slower? Why am I slower than the .NET dictionary? I came and just looked at it. And that's what I'm doing here is I'm looking at the source code for it. And one of the nice things you can do is you say like, hey, document outline. And this makes it a little easier to search around. And I am wanting to look up the find value method. So because that's what our benchmark is looking at. It has populated dictionaries and it's just looking up values that are in the dictionary. That's the only behavior we are benchmarking right now. So I'm like, okay, why is the .NET one faster? That is a great question. So what's going on is like, okay, it says find value and it's passing in a key of type T key. And it's checking if it's null, throwing an argument, null exception if it is null. It's getting this unsafe ref. Okay, it's checking that the buckets, so the underscore buckets is the backing array for the .NET dictionary. And we've got a debug assert. And then it's doing this like null check comparer thing. It's like, wait a minute, what? It's looking up saying like, hey, do I have a comparer? And then it's saying, hey, if this is a type of, if the key is a value type and the comparer is null, it's going to use this code. Huh. Okay. So value type. So this would be things like int, float, like the numeric primitives or structs. And I have a video on structs now if you want to go check it out. So like these are the value types. These are things that would be like stack allocated. And it's saying, hey, do I have a comparer? Because you can pass in a custom comparer to the .NET dictionary. So that's what it's basically checking for here. And then it's got some code for like, okay, I'm going to go get the hash code. Whoa, go back. And then it's going to get the bucket and it's going to search the injuries. Okay. And it's checking for number of collisions. And then it's doing what you see in our code. It's like, hey, if the hash code, okay, well, let's see if it actually matches our code. Like, okay, it's checking if the hash code's equal. And if the equality compare.default.equals, like, hey, that's interesting. Okay, we know about this because when we did our zero allocation thing, we were wanting to get rid of allocations. And we remember to do this. But this is the branch for value types. So remember in our dictionary, our Fibonacci hashing version, integers are value type and they are faster in our dictionary than the .NET dictionary. So I'm actually not as interested in this branch. I'm interested in this branch. What is this branch doing that is different? And what it is doing is like, okay, it has compare is not null. Wait a minute. What's going on here? It's using an existing comparer versus equality comparer default.equals. What is going on here? Why is it using this existing comparer? That is a great question. So let's talk about this. So let's see if the hint is in here. Okay, so what it's doing is it's saying, hey, if it's a value type and we use this equality comparer.default, it has the .NET runtime has a possibility of inlining that equality check. But it doesn't for reference types. And so what they are doing for performance here is they don't want to create a new instance of the comparer each time. So it's keeping a copy of the comparer object around so that when it's going through its loops and doing these lookups, it's not having to create new objects to do this comparison. So this is the trick that they are using to go faster than ours. So if we go back to our code and we look at what are we doing in Fibonacci hashing, we are not keeping an instance of a comparer around. And so when we want to go get a value, we are always using equality.default.equals. And so we, for structs, for value types, this method call can be inlined, which is why our int dictionary, the int keys, is faster for us. This is all getting inline for us. And it's probably getting inline for the .NET dictionary as well. It's just like our logic appears to be faster at this point for integers. For reference type those, it can't inline this at this point. And in fact, it's probably having to like new up some objects to do this equality check as well. And so that's adding a lot of overhead to our inner loop. That is no good. We want to get rid of that. Okay, so what do we do? Well, we are going to copy the style that the .NET dictionary is using, and it is in the cache equality. And so this it should be maybe it should have been called caching equality because it's not like an L1 cache equality, but it's like it's caching the equality comparer, compare object. So that's really what it meant by caching it, not like cache as in the memory, but cache as in like keep a copy around. So the way this dictionary has changed now is when we create an instance of our dictionary, it's saying, hey, if the type of the key is a value type, we're just going to return the default object, which in this case is just going to be null, right? Oh no, nulls. But don't worry, we would never actually use it if the key is a value type, because we're going to have a logic later which is going to switch on the key type. So potential danger here, this is returning null. Don't worry though. And oh, there's another trick that they are using that is very clever and kind of annoying. So if we go and look at where this comparer is being stored, go way back up to the top, we see, it's like, hey, when you create an instance of the .NET dictionary, it's saying, hey, if the key type is not a value type, so you notice that they had this bang operator here, if this is not a value type, then we want to create an instance of the equality comparer, and they have another check here. If the type of the key is a string, they are going to get a string comparer. So not only are they like keeping a copy of the comparer object around, they're getting a specialized one in case of a string. Okay, well, what's the logic inside of that? Because that's exactly what we are doing. Like we have strings as keys, and so is this what's giving them so much more performance? It's not just the fact that they're keeping an instance of the comparer around, it's a super special comparer. So it says get string comparer. Okay, what the heck is this? And object comparer, wrap around default comparer, wrap around string comparer, ordinal, wrap around string comparer, ordinal, ignore case. Oh my goodness, lots of things go on here. The important thing to note is that, hey, I'm going to give us a little bit more room here, is they have these different string comparers that they can use and that they will use in different situations. Now, this is where I'm telling you the .NET dictionary is a fantastic dictionary. So it's a great default. Do not take this series as me deprecating the .NET dictionary. It is fantastic. And part of it is it's protecting you from things that you don't even think about. Well, probably don't think about. And one of them, it comes back to our Fibonacci hashing. Remember how if you put in a set of keys that have like particular patterns, it can cause very bad behavior because all of the keys are mapping to the same bucket in your backing array. Well, strings are so often used as keys in dictionaries, they are definitely a vector for denial of service attacks, where the person trying to do the DDoS will send requests with strings that are of a particular pattern, which they know will cause problems for dictionaries, right? Because they know they will map all to the same bucket. And so just by virtue of the fact that like, hey, now all your algorithms that used to be O1 are now ON or something other horrible, it's a way to do that. So what .NET does, it has randomized string comparers. And so for each instance of .NET, like it has some randomization mechanism so that those patterns that people are trying to inject and cause a DDoS attack on you, it's using a random way of sorting those strings and hashing those strings so that that doesn't actually end up happening. So that's fantastic. I'm not going to add that to my dictionary because I don't care about it for the particular scenarios that I am working on, but it's something to keep in mind. Like it's part of what makes it great. That's why they have multiple different string comparers here. And what I want to go to wrap around, okay, ordinal comparer. Let's look at this ordinal comparer, equality comparer, wrapped comparer, get non-randomized hash code. Okay, so this is what the super high performance for strings command. What does this thing look like? clicking on it. Oh, goodness. Pointers. There are pointers happening now. So what this is doing is it's like, hey, I'm taking a char pointer, and now I am iterating through that string and using bit operations and rotates in order to hash this string very quickly. So this, again, is part of how the .NET dictionary is getting better performance than our dictionary when it comes to looking up keys that are strings in our dictionary. Well, that's some wildly convenient cheating going on. Not really cheating. I mean, this is what we call engineering. You design for common scenarios. And so we would like this in our dictionary. So let's borrow it. We'll come back to our code now. And we see, okay, cool. If the type of the key is a value type, we're going to use what we already have, because that gives us the possibility of inlining that method call. If the type of the key is a string, we are going to use our string comparer, which I will talk about in a moment. And if it's not any of those, I am just going to cache. I'm going to keep a copy of my reference comparer in my dictionary. And that's what I'm doing here. Let's look at what string comparer looks like. And it's actually just right above that code that was there. It said, hey, string comparer. And now I'm using an F# object expression. And what I'm saying, like, hey, I'm going to create a new instance of the I-equality comparer of type string. And I have to give it two methods. One is the equals. And so the equals for this is just the default string equals, which is very fast because it checks like, hey, is this referencing the same place in memory? And if it isn't, then it will do some other tests, but it's a very fast string equals. We can't really improve on that. And we are just going to straight up steal their code for computing the hash of a string. So this, I took exactly what the C# was, and then I put it into F#. So now we have our fast string comparer. And so when I swap these out, when I'm caching this reference comparer, I need to change my code a little bit so that I can choose the different ways of doing comparison. I'm going to go ahead and collapse add entry because that hasn't really changed much. But now when I want to get a value, what my code is doing is it's saying, hey, is the type of key, is that a value type? And so I'm essentially taking what that C# code was doing, and I'm now doing an F# and on my data structure. And if it is a value type, I'm going to use that default equality compare in hopes that this get hash code method is inlined. And same thing with the equality compare default equals for value types. We're really hoping that that method call gets inlined. And if it's not a value type, then we know it's a reference type. And so we are going to use our cached reference comparer. And so that's why we don't worry about the fact that, hey, this ref comparer is going to be null when the key is a value type, because in our method calls, we're always kind of switch. We're going to test, like if it's a value type, use this code that doesn't use that reference comparer. If it is a reference type, then yeah, we will use the reference comparer. But in that case, we know we will have created an instance of it when we created our dictionary. So again, same logic, but now I'm using the ref compare in both in the get hash code method and for the equals test. So when I use this code, what do the benchmarks show? Great question. Now, let's first look at string down here. So now I have my cache equality dictionary, and now for 10 entries, we are faster. For 100 entries, we are faster. For 1,000 entries, we're not as fast, but we've kind of closed the gap. And for 10,000 entries, again, we are still slower, but we have significantly closed the gap. I mean, this was 980 before, and now it's 547. So we've gotten better, still not fantastic, but what should really kind of get our curiosity is like, the performance for the integer type has gone down. Like it's worse, it's taking longer. Because before, this was 40 microseconds, and now it's 58 microseconds. That's not good. So it's 48 microseconds for 100 entries and 64. So why did the performance for int get worse? That's a fantastic question, which I will answer on Wednesday because we're already at 20 minutes. Thank you so much for spending some time with me. I hope this was interesting. I'm really enjoying kind of diving deep into this subject. And if you have any questions, please feel free to leave comments. If you have things that you want me to dig into, to kind of uncover and go into more detail, please let me know. I'm making this for you. I'm trying to be helpful. Also, I found out that I have more work time available to me than I realized. At the consultancy I worked for, didn't need as many hours. And so instead of kind of going and getting an enterprise job or some other company, I said, like, you know what? I'm just going to take this as an opportunity. I'm going to see if I can make it as an independent F# consultant. And so I specifically focus on high performance simulation and optimization. I write algorithms for scheduling and planning. So if that's something that would be of interest to you, please feel free to reach out. Thank you for spending some time with me. You have a great day.